And I want to make one comment about the overhead that we get from doing by doing code concatenation. So I said it's polylogarithmic in n, and one thing one can worry about is the size of this overhead, this power of this log n. But in more sort of, it would be ideal, of course, if the overhead would be constant instead of something like log n to some power. It would be just proportional to n. And I'll make a comment about that later in this lecture, and that there may be, it is a possibility that this can be done, and it's some recent work that appeared on the archive. Okay, so I have not talked much about how to do computation on encoded qubits. And so we'll start with some observations concerning that.
I can't do this non-invasively. I'm getting ejected.
Okay. So ideally, gates are done as transversal gates. The transversal gates show it like this. We just do the gate that we would do on unencoded qubits n times on the encoded data. Because why is this very good? Well, there is not no overhead in terms of needing additional ancillas, and there's no spread of errors, right? If one of these gates fails, then of course there may be an error on both blocks, but none of these gates will put, if one gate fails, there will be an error, two errors on one block, which is of course a property that we want for fault-tolerant gates. We don't want a single error somewhere to become two errors in one block. So ideally, we would be able to do all gates by transversal operations, and for the classical information, that can be done. So, for example, if you use the classical repetition code, you just repeat all the gates, n times, and that you repeat all process n times. That's the way to do it. But there is a theorem that for stabilizer codes, not all gates can be done transversally. So you need other constructions to do certain types of gates, and these constructions you'd like to minimize the cost in terms of overhead and in terms of noise threshold. So the problem is that complicated non-transversal gate constructions can depress the noise threshold because they involve many circuits with many locations where errors can happen. So in order for that circuit to function well, one has to start with a very low error rate. And the ideas that at least we envision how we going to use the surface code that are very good are different ideas. One is the idea of code deformation. The other one is the idea of doing gates by injection and distillation.
I can't
yeah, sorry.
Transversal gates. Transversal meaning of transversal. Is it related to control gates or?
No. It just lays like if I do a Hadamard, for example, I have to do a Hadamard. Then it's transversal. If the way to do the Hadamard, just do a Hadamard on every qubit in the block. So it's blockwise. So I just the original gate that I needed to do, I just do that, n times.
Independently.
Yeah. Now there are slightly, there are modifications that may be, okay, that's the it is the very narrow definition of transversal. Yeah.
Where do you put magic states?
That is here. Okay, but I'll say something more about that. Yeah. The idea of code deformation, which we'll see in the surface code, is very nice, and I think can be further explored actually. So the idea there is that you encode your qubits in some code, stabilizer code S, and by doing some operations, maybe it's a unitary operations, maybe it's some measurements, you map that code onto a code S prime, which is slightly related to it. And then you do further steps that map it onto code S double prime. And you do that until you get back to the code S. So maybe that number of steps can be, you know, just 2. You get to a code S prime, and then you get back to the code S, or it can be a whole sequence of transformations. And you could see that if this is if the code were realized as the ground space of some Hamiltonian, and then you could see this code deformation as a deformation of the Hamiltonian and its ground space, right? So you start off in some ground space, in some code space related to their first stabilizer. Yeah, sure.
I'm wondering whether the fact that you cannot do things by traversally for stabilizer code, doesn't that give you also a bound in the number of steps you need to do to deform? Because two-step deformation sounds to me
As to, yes.
to get universality.
I don't know whether that is a good question.
Deformation,
yeah, I mean, of course, the thing is that, yeah, what do you have to be a bit more precise? What do you define by deformation? For example, if you do a Hadamard gate for the surface code, you get to the new code, but then you have to do, yeah, it's not in order 1 steps. It's
usually it's logarithmically many or something like that.
It's something that scales with the block size of the code. Yeah. Yes. Yeah. There are more results related to this, how you can optimally do encoded gates. There's some recent results by Bravi and Koenig on this, but they're not related to transversal gate, but more to code deformation. Okay, so some gates can be done, as we'll see, for the surface code or for other topological code by code deformation. And this code deformation idea, it turns out to be also very efficient in terms of not needing more ancillas and also not having any effect on the noise threshold. The second idea, but then there may be gates that you cannot yet do by this code deformation technique. And there is a scheme that we invoke, which is a scheme of injection and distillation. And maybe at some later stage, I'll sketch you this sort of the ideas that go into that. So I want to motivate why I spent hopefully spend a considerable time in this talk on the error correction with the surface code, and it being just a stabilizer code. And why I think it's important to, if we do go this route, if we imagine that the surface code or variants thereof are the ones that we can realize experimentally, why we should focus on a quantum memory or a quantum memory plus. Because this is very natural in that architecture. Now, so some people may be completely familiar with this, that there are, in terms of how you have to do computation, there are gates which we call the Clifford gates. And the Clifford gates is a subset of the unitary gates. They're the Hadamard, the C0, the S gate, and the Pauli's. These generate the Clifford group. And the properties of these gates are that if I have a Pauli operator on many and n qubits, and I conjugate it with a Clifford, then it will become another Pauli operator. So if I have a circuit, so this is the basis of the Knell-Gottesman theorem, if I have a circuit which only has Clifford gates, I can actually classically simulate this circuit by following basically the stabilizer of the initial state of the circuit. This is a basic theorem in quantum information theory. So for stabilizer codes, it turns out that some Clifford gates can be done with minimal overhead. The C0 and the Hadamard we will discuss. But then we need let's focus on the surface code. In order to get universal set of gates, we need to do the S gate, which is also a Clifford gate, but cannot be directly done using code deformation techniques for the surface code. And we also need to do the T gate to get universality. And so for that we invoke an idea this is this injection and distillation. But the point is that the overhead in doing this such a T gate is very, very large. So, for example, a single realizing a single encoded T gate requires hundreds. This is a rough estimate because these numbers are changing because there's work in improving this. Hundreds of noisy T ancillas. So, and these noisy T ancillas are single qubit ancillas. So there is a much larger overhead. So that's the one reason why I think if we go the route of stabilizer codes, it's a sort of a two-step process where one can imagine that at the first step we build something like a quantum memory, and the second step, which is really, quite a bit more involved in terms of, practical complexity, we build a machine that does actually computation that we cannot simulate classically. And so the one reason that it requires more complexity is that the overhead for doing a computation for overhead for realizing T gates and so on is sizable, is much larger than for the C0 gates. And the second thing has to do with decoding. And so the thing is, the observation. Let's see how I can pinch you with that. So the Knill. So I don't know if people have heard about this Knill-Gaussman theorem, but the thing is, you can if you're only doing Clifford gates. So let's imagine I do a computation. I only do C0s and Hadamars and Paulis and so on. Then if I, for example, based on my decoding, at some point I have to correct and do a logical Pauli because the environment, implemented that logical Pauli, and I just have to undo it. Yeah. But then after that, the only gates I'm going to be doing are Clifford gates. Yeah. Then I can commute this through. So I can just insert. Well, I'm not saying this so clearly. I can commute this through, and I can just keep track of what we call the Pauli frame, and not actually do the correction. Yeah. So there is, and actually, I want to make one comment about that. So there are two. This Pauli frame consists of two parts. One is I want to be in the +1 eigenstate of all the stabilizer checks. Yeah? And sometimes I have an error happening, a Pauli error, and I'm not in this +1 eigenstate. But I mentioned to you that any other space characterized by these eigenvalues, if that could be -1, +1, is an equally good code space. So so if I'm not in the original code space, but I'm in another code space that is related to this original code space by some Pauli pi, then that would be fine. Well, I can write that down on a piece of paper. I never need to do that correction. I just need to know that I'm not in the original code space, but I'm in the code space labeled by different eigenvalues. Errors do accumulate, so I keep track of these Pauli corrections that I should have been doing, but I'm not doing. Yeah? And at some point, they accumulate such that a couple of them, the product of them, becomes illogical P. Yeah? And because these are just elementary Paulis, and the logical P is something that is more long range. Yeah? Now, if I were to do Clifford operations, I don't have to implement this logical P. I just write it down on a piece of paper, and I do the correct interpretation of my results, assuming that, instead of having a 0, I really have a 1 now. That's fine. If I were to do T gates afterwards, so these non-Clifford gates, then I would really have to implement this logical P. But I never need to implement these corrective Paulis. Yeah? So, so the point of decoding is that errors accumulate at a certain rate. Yeah? And I am interpreting, I'm guessing what errors happened at another rate. But if that last rate is lower than the first rate, I will be behind once it's time to realize my logical P. So I need my decoding has to be done at the rate at which errors accumulate. For if I want to realize universal quantum computation, not if I just have to do this Clifford substrate. And that is an essential point because the decoding is not necessarily very fast. Because what does the decoding do? Well, it depends on how we realize this, but it may, if it's something that we have to get the signal out to our world and then process it on a classical computer, it's a question whether the clock speed of this classical computer is fast enough to do this decoding faster than the errors accumulate on my 1 nanosecond gate, quantum computer, which is the clock speed is pretty fast. I think for the superconducting qubits, it's like 10 nanoseconds, single qubit gates. Okay, so that's why there's a complexity. I would like to make a distinction in terms of complexity of doing one versus the other. Of course, if we build this Clifford substrate, we haven't done anything that we could not. We could do it all classically, and we haven't done anything that's computationally more powerful. Okay, so now I'm getting ready to talk a little bit about the surface code. So there's some pictures by this paper by Dennis et al., which I think has gotten to be a paper that has increased in influence over time, of being recognized for its value over time very nicely. But before I do that, I want to motivate why I have this focus on the surface code by this sort of overview, which probably doesn't do justice to everything. And maybe this is all going to be irrelevant once the experiments are are sufficiently advanced to realize some quantum error correction. But just to put things in perspective. So here are some pluses and minuses that I note of various schemes. This font got messed up. There are so the surface code is an example of a two-dimensional topological code. There are other topological codes, like color codes. And they have both advantages and disadvantages. Some of the disadvantages are that the parity checks involve not 4 qubits, but more than 6 qubit operators. So then you say, well, if I have to realize it may be more challenging, the noise rate may be higher and I have to take that into account if I estimate a noise threshold. And an advantage is that one can do all the Clifford gates, so also the S gate, in a I say topologically, which is by code deformation, or transversely. Yeah, so so the S gate is included in this. The noise thresholds are a very similar range as the surface code, so in that sense, there's no difference. There are also two-dimensional subsystem surface codes, or two-dimensional subsystem topological codes. And one nice proposal was by Bombin, Poulin, Bravi, and Sucara, which defined a subsystem surface code where you the parity checks are weight 2. And so remember that Bacon-Shor also had these weight 2 parity checks. Those were these non-commuting checks, and you had to combine information about them to get the stabilizer checks. In this case, it's also weight 2 parity checks. And the noise threshold is actually, I haven't told you the noise threshold of the surface code, but it's very high. It's order 0.6%, which is very close to the surface code, because their surface code is about 1%. Well, depending on, yeah. But the one disadvantage of this code is that the qubit overhead is large. So, for example, for their smallest code, you encode 1 qubit in 41, and you have, what's this? Yeah, there's, it corrects, no, wait a moment, what is this number? This is not DS1. There's something wrong about this, but okay, so I think the overhead is larger. If you say I want the smallest non-trivial, I think maybe this is correct. This is the smallest non-trivial code, because if you compare it to the 913, this is very, very bad. Here again, the C naughts and the H can be done topologically. It's similar as the surface code. Now, to go beyond the stabilizer formalism, there are also codes which relate to two-dimensional 11 Venn models, and they have been looked at as Terhal codes. There's beautiful mathematical theory behind these codes, but we have not understood, at least so far, very much how we could use those codes explicitly as codes and do error correction with them. One issue, for example, well, one thing that has been established for some codes that you have to measure very high weight parity checks, if you write it explicitly as parity checks. How we do error correction in terms of how we do decoding for these codes is something also that is a subject of current research. And I don't think a threshold has been estimated for classes in these classes. The advantage of these codes is that one gets a universal set of gates by, I say by code deformation, but because these are related to non-abelian anyon models, if they relate to non-abelian anyon models, one can get universality for all, more directly. Okay, so these are all two-dimensional codes. One can also say, well, what about one-dimensional codes where qubits lay on the line? And there the distance you can prove over stabilizer codes, the distance is order 1. So that's not very useful. The Bacon-Shor code, another two-dimensional code. The advantage is that you measure these weight to parity checks. One possible disadvantage is that it's a non-topological code. What it means effectively is that if you take this class of codes and you make n larger and larger, it doesn't go to a finite noise threshold, but the noise threshold goes to 0. And there's a way of understanding that you don't, in order to have a finite threshold, you have to be able to correct a finite density of errors. And here you're correcting not a density of errors, but something that scales less than a number of errors that scales less than the block size. That's a short comment about why these codes don't have a asymptotic threshold. But there are interesting studies that show that for small block size, these codes actually may have better performance than the surface code, or at least competitive performance as compared to the surface code. And of course, we're not interested in going into infinity. We're interested in a finite n.
Mm-hmm. And the Bacon-Shor code is first in the 90s. Is this ordered by time? What roughly is when these things?
No, there is not. Okay, so this is after the Dennis, 2004. It's hard. This is very recent. There are other more recent. We did some work on 2D subsystem codes, but they were not so competitive. They had much lower threshold. This is 2 years ago. And these 11 Venn models are also older, and Terhal is also less than 5 years, I would say. It's not hard. The Bacon-Shor, I think John Prescott has done some fairly recent studies, also in the last 2 years, on the Bacon-Shor codes. So these are developing subjects. It's not like this has all been sort of settled. And like these... I think for QIC this year, there were some error correction algorithms, decoding procedures for codes which involve non-abelian anyons. And that's the first time that has happened. Okay, so now that I hope I have motivated a little bit why I want to look at a surface code, because, first I haven't mentioned anything about 3D or 4-dimensional codes. Yeah. And there's also a lot of work on that. There are 3-dimensional and 4-dimensional versions of the Toric code, and there are other interesting 3D codes. But we leave that aside now, so that we could discuss that also. But okay, so I hope I have motivated why the surface code is why I sometimes call it the sort of modern Ising model, in the sense that I think it's a model which demonstrates the features of topological order, coding in its most pure, simplest form, and for two-dimensional, stabilizer codes, you can also show that, any, say, like some of those other codes, that the decoding procedures can be viewed as a way of decoding the surface code. So it has a certain universality. Okay, so I presume that you've heard something about this, so I won't go through this. I won't spend too much time on explaining it. But so this is a surface in 2D, and the qubits are on the edges. And the code is defined by defining the check operators, which are the stars and the plaquettes. And at the boundaries, we need to take these to be weight 3 operators. And so the smallest code, for example, you could consider is the code. It codes 1 qubit into 13, and it has distance 3, so it corrects 1 qubit. And that looks immediately, you can see that's less efficient than the 9 qubit code, or the 7 qubit code, or the 5 qubit code. And that is something that is a disadvantage of the surface code, in some sense, that there is it's not so efficient in terms of space, and its performance, only sort of good performance, shows up when you have a lot of overhead. So when you encode 1 into many qubits. Okay, but I'll come to that also. Okay, so the checks are these operators, and so that you can say what are the operators that commute with the checks but are not generated by it. And these are the logical operators. The logical z is along this line. The logical x is along this line, and you can deform these to go like this. But the important property if this is a surface is that the logical z goes from what we call the rough edges here to the rough edges there, and the logical x is going from the smooth boundary to this smooth boundary. It cannot stop in the middle, because if it were to stop in the middle, then it would not commute there.
Where is the 13 in this picture?
Oh, well, no, this is 85 LS7. Sorry, the number of 13 are the number of qubits, so it's just the number of edges that I have in this lattice. Okay, so so one thing this you can skip because we've already talked about it. So there is the surface, so this is the surface code, but it's directly related to the Toric code. In the Toric code, I just close the boundaries in 2 ways. Yeah? I make this lattice on a torus. And the surface code then encodes 1 qubit, and the Toric code encodes 2 qubit, because you actually have a linear dependency between the parity checks for the Toric code. Okay. Did I already say? Okay. So this is a picture from this Dennis paper. Because you can view, why is this a topological code? But it's not so clear when you talk about the surface, but it's much clearer if you think about it in terms of this Toric code where you close the boundary. Because in that case, the logical x and the logical z are non-trivial loops around the torus. What are the elements in the stabilizer? Well, for example, if I take z checks, these plaquettes, and I take products of them, I can make a loop like this. That's a trivial loop on the lattice. While the logical operator is a string like this. It's a non-trivial loop. Okay. Okay, so so I mentioned this rough boundary and the smooth boundary. And you can also quite easily understand that the distance of such code is L. because the logical operator has to go from one boundary to the other, and it cannot terminate in the middle, otherwise it doesn't commute. And the minimum way to go from one boundary to the other is to go over touch these L qubits.
What is rough boundary and smooth boundary?
Well, this is just the definition of this is rough because it sticks out. Say, here there are the Z checks. There are checks on these 3 qubits. There's no qubit there. And here we call this smooth because it's sort of smooth. It's just a convenient wording of the difference between these 2 boundaries. Okay, so so what happens when when errors occur? For example, I have some Z errors that happen here. These black line, there's 3 Z errors here. And what kind of syndrome would I get? Which parity checks would now have some non-trivial eigenvalue? Well, it will only be, only the X checks, because it's a Z error, and it will be only this one. And similarly, if I'm talking about X errors, going to the boundary, I would have a non-trivial -1 eigenvalue here. Okay, so okay, why am I talking about, yes. Okay, so before I talk more about how we process these errors, how we do decoding, I want to say something about what would we do with such a quantum memory? How would we get it started? Yeah? In a very concrete way. Right? Because we want to tell the experimentalists, if they have a bunch of qubits laid out, how could they encode some information state into the code? Now, because I'm only talking about quantum memory, I just say, well, we want to just we want to just encode, say, a 0 or a plus or a logical 1 or a logical minus. Of course, and I am not covering that in this talk, you can also ask, well, let's imagine that I have a qubit is given to me, via some means, and I want to encode it in some unknown state psi, and I want to encode that into my surface code. Yeah? There's also a way of doing that. But here I'll just show you how to prepare the quantum memory in one of those 4 states. And then you say, well, and then further, if I want to have another state, I just need to act with gates on it. So the way you do that, so let's look at that for the logical 0. What we do is first we know that the logical 0 is a unique +1 eigenstate of all plaquette and star operators and the logical Z. Yeah? Right? There's a state in the code space, but if I fix the eigenvalue of logical Z, I get only the 0. So what we do is we prepare all qubits in the state 0, and we note that all 0 is already a +1 eigenstate of all plaquette operators and the logical Z, right? Just by definition. So we're sort of halfway there. Yeah? So what we do is we start measuring, we could measure the Z plaquette operators and see indeed they get +1 eigenvalue. What we do, we measure all the X star operators as well. And these X star operators will have random eigenvalues. Because these states, if you just look at 0, 0, 0, 0, and you look at the eigenvalue of this X check, it has randomly eigenvalue +1 or -1. So in some ways, there are many errors on this system because there are many places in which these X operators come out to have -1 eigenvalue. So we need to correct these. But the point to note is that how we correct these, by doing some poly Z's. Yeah? And we say, well, do we need to worry about what poly Z's we correct them, we use for the correction? The answer is no, because note we're making a state that has, it's a logical Z. Everything we do with these Z's commutes with this operator. So we'll never make a wrong error. We just take any correction that will that is possible, and make sure that all these star operators have +1 eigenvalues. Yeah? So that's a procedure we do if we assume that measuring these check operators is noiseless. And I'll come to, there's a simple way in which we alter that procedure if the check operators, the measurement of the check operator is noisy, and that's basically repetition. And we'll do for all steps, every procedure that I'll discuss on the surface code. If you assume that the basic steps are noisy, you just make it more robust by repeating. Okay, so the measurement of the logical z and the x is the reverse of this operation. So for the measurement of logical z, you measure all the qubits in the 0-1 basis, and you determine some error information, and then you estimate the eigenvalue of the logical z. Right? That's the measurement of logical z, is determined whether the eigenvalue is +1 or -1. Okay. So that's the So now this sort of the overall view of this quantum memory is to have something as basic as this. So first we encode bare qubits into a sheet. Well, I call it the sheet. This is a surface. And to stress this point that we never need to do any corrections, we could think about it as follows. We continuously do parity check measurements and collect syndrome data. We don't do any correction. We just collect this. At the end, we decide to do a measurement in logical z or logical x. I'm just assuming that we encode 1 qubit here. And then we process at leisure the syndrome data record to determine, to interpret the outcome of this measurement. That's the whole procedure. So that's this sort of quantum. Okay, that's at least without any further gates. Okay, so now the circuits, so the check measurements, we already saw this before. If you have the plaquette or the star checks, they're weight 4. So they need either some direct realization or some implementation using, say, 4 C0 gates and some Hadamars. And one can also, if you're interested in sort of really thinking about how this looks like in terms of a 2-dimensional array, one can imagine that this is done efficiently in the following sense. So the black dots are the data qubits of the code. So they are on the edges. And these we put ancilla qubits on the plaquette and on the vertices of the lattice. And this picture is a little bit confusing, but the idea is that while we do some C0s for the Z plaquette measurement, actually, is this the Z plaquette? No, this is actually the other one, I think. Okay, we do well. Okay, so the thing is that you can imagine that it's fairly efficient to if you put ancillas here and there, to use those ancillas to do a Z plaquette measurement, and you use those ancillas to do an X measurement, the star X measurement. But I'm actually confused. Oh, I know why this lattice is. Oh, okay, yeah, this is confusing because the original lattice is not this one, so I shouldn't use this figure. Okay, but you can do this fairly efficiently. Okay, so now let's talk about how we do decoding. I discussed in the first lecture what is minimum weight decoding. Minimum weight decoding is choosing the error that has minimum weight, which is consistent with the syndrome. You can generalize this to maximum likelihood decoding, which I didn't mention too much. So maximum likelihood decoding is just saying, well, what's the error or the error class that has the highest probability of happening. But let's not discuss this right now. Okay, so we want to discuss how we do this in the case the syndrome measurements are noise-free. These parity check measurements are noise-free, and in case they are noisy. Now, so because this code is such that we have the Z checks and the X checks, they're actually the same if we change the lattice to a dual lattice, the decoding is completely analogous for both of them. So we have two identical decoding problems which we could solve separately. Now there may be a correlation between the two, because if you have a Y error, you both get a Z and an X error. So it depends a bit on your error model. There's some optimization you could do. But in principle, you could just say, I'm just looking at the Z checks and I determine what's the most likely error, right? What's the most likely X error that I infer, and I'm looking at separately at the X checks, and I look what's the most likely Z error, and I don't look at possible correlations between those. Okay, so as we, if you remember from the first lecture, we had a criteria for when decoding was good or bad. So decoding was good when the real error times the guessed error was an element in the stabilizer. So in this case, it should be a trivial loop. So if we have a string like this, let's say that's the error string. All these qubits underwent an error, and those are all Z errors. We detect at these 2 points where this string ends, we'll get a non-trivial syndrome. And on the basis of that, we decide upon this error string of low weight. And you see then we make no error. It's a good decoding because the product of this error and that error is this trivial loop. Similarly, for the with this on the dual lattice, now we have a string of X errors, these gray ones, that goes like this, and we have non-trivial checks here. And instead of inferring this error, we could also infer, say, this error string, and that would also be fine. So that gives us a lot of freedom. And so you could see that if you call these places where the syndrome is -1, you call them defects. So there are 2 defects here, and you notice that if errors happen, and this is on a torus, that these defects always come in pairs. Right? It's just the endpoints of the error string. That a good decoding is annihilation of the defects in a trivial way, without making a non-trivial loop over this around the torus. And the bad decoding is, for example, this, where I have this error string all the way there, and instead of inferring an error that goes from there to there, I take the green error, and then it's clear that the product of these 2 errors is a non-trivial loop around over the torus, and therefore I've inadvertently made a logical error. Yeah? So you can say that also that this pair of defects is annihilated by a non-trivial path. Okay, so now, yeah, there is some fonts that were messed up, unfortunately. Okay. Okay, so so minimum weight decoding. So the thing is that I argued in the first lecture that if you use minimum weight decoding, you can correct any number of errors up to the distance over 2, approximately. And the distance here is L, so that's L over 2. And that actually doesn't look so good, right? Because if I have an L by L lattice, and if I can only correct errors up to, say, order L, then the bigger I make the lattice, the fewer errors, the lower fraction of errors that I can correct. So that would mean that for L going to infinity, my noise threshold will go down. My logical error rate would actually go down. But that's not the distance of a code, especially of these topological codes, is not everything. At least it says it has another stronger meaning, because you can also imagine, we can correct potentially more errors above the distance. It depends on just what these errors are. If I put random errors on this space, so it's random single or 2 qubit errors like this, you can imagine that I can very well correct this, as long as this density of error is sufficiently low and these pairs of defects are separated, because then it's quite clear how I should annihilate them. I just have to locally pair them up. So what that means is that I could correct a constant density of errors, as long as that density, that's called alpha here, below some critical noise threshold, alpha critical, it can still be corrected. So the code can correct typical errors of weight alpha times L squared. The typical, of course, if all these errors would sort of line up on the line, I could not correct it necessarily. Okay, so that is the motivation for that you expect this behave as there's to be a phase transition in this basic error rate. So we assume that every qubit undergoes some X errors. And we only look at the Z checks, the measurements, and we believe that, or what I tried to talk you into, is that if you take this L going to infinity, that we have to see the following behavior. Below some critical value of P, most errors will be successfully decoded and corrected. So the logical error rate will be 0. While above this threshold, most errors are not successfully corrected. And this phase transition also has been studied in detail in this paper by Dennis et al. So the goal then, now you can say, well, how hard is this decoding? Because I also said we may anticipate that if we want to do universal computation, this decoding should be done efficiently on our classical computer or by some other means. And so the one way in which we can do decoding is the following, but there are other, potentially faster decoders. So let's imagine we have an even number of defects, meaning that we work with the Toric code. If we have the surface code, we can have an odd number of defects, because we can have something where the surface code is like here. I can have a bunch of errors here, and it terminates here. So there's a string of errors here, and there's a defect there, and it's a single defect, and sort of should be matched with a defect in this boundary. But in the Toric code, I don't have a boundary. So I have an even number of defects, and I want to match them. So I want to pair them up such that I minimize the distance, the overall distance, the sum of the distances between them. Now, you have to define some distance. It could be a taxi cab distance. And one way of then doing this decoding is to use what's called a minimum weight perfect matching algorithm. So it's an algorithm which has a set of 2 endpoints, and distances divided by these between these points, and matches these points such that the sum of all the distances is minimized. And that algorithm scales efficiently. It's polynomial in n, but if we apply it for such a lattice, it may still be quite inefficient in terms of requiring quite a bit of time. But as we argued, if we have a quantum memory, that is not really a problem. There are other faster realization group decoders. They've come around in the last 4 years. Which have, I think, sort of a pleasing, intuitive picture, and their performance is pretty good, not as good as the minimum weight matching. And they're the following procedure, where you say, well, I kind of divide the lattice up into blocks and into cells, and I start with a very small cell, and I see if in such a cell there are an even number of defects. And if there are an even number of defects, I pair them up. And that just cost me some order 1 time to do that, because it's a small cell. And if there's an odd number of defects, I know that, or say there's only 1 defect, I have to pair that guy up with another cell. So after I've done this first round, where I've removed some of the defects, the ones that could be paired up, I enlarge my cell size, my window, make it twice as big. And then with the remaining defects, I start pairing those up. So now I get to kind of pair up defects over a larger distance. And again, I will have some defects which are, odd number of defects in this bigger cell size. So then I go to a larger cell. So that's the rhythmization group decoder idea. At least that's the sort of version that was proposed by, I think, written down by Bravi and Ha, and first thought about by Bravi. And those are more efficient, although in order to get a noise threshold to get food performance, you need to make the cell size of order of the lattice of order of L. An L by L, order L by order L size cell. Okay. Okay, so now so there are 2 things what you say now. If we talk about the threshold, we can estimate the threshold if we assume the parity check circuits are noise free. Then it's been shown that this critical threshold noise rate is very, very high, 11%. And then you say, well, what happens with, in the realistic case, we have noise errors in these circuits. Yeah? And what we see also that if we have errors on ancilla and so on, we can feed back errors to the data. Actually, not necessarily to 4 data qubits, but to some data qubits. Yeah. Is that bad? Well, in this case, it's not so bad, because we imagine that this L is fairly large. Yeah? And so what we have is, so if L is sort of large, instead of having, single qubit errors happen somewhere, you'd have some kind of, cluster of errors. Yeah? But if still this density of cluster is sufficiently low, I can still do some correction here. So so you can imagine that you don't want to replace, so in the others, I said for the 7-qubit code and so on, we argued we need a more complicated ancilla. And for this scheme, you can say, well, we don't necessarily need a more complicated ancilla. It will have an effect, but we can still, we don't get more errors. We don't generate errors above the distance of the code by doing this, which with the 7-qubit code was not true. Using the ancillas, we generated 2 errors where the code could only tolerate 1 error. So the other effect, so one effect is that we generate more errors on the data. The other effect is that the syndrome may not be the correct one. Yeah? It's a faulty error syndrome. So then that solution is that just to repeat the syndrome. Yeah? So you like to use a repetition code where you say we want to know for sure that the syndrome bit is reliable. So how does this work? Because the idea here is this. The decoding of this noisy syndrome is actually also a matching of defects, but in a 3-dimensional space. Yeah? So before we had defects on a plane, and we have to match them pairwise, and now we have defects in some 3-dimensional space where we have the surface code and then the time direction. And let's mark by red places where the syndrome value changes, assuming that initially the syndrome value was all plus, was perfect. Yeah? So if we see something like this, let's see, something like this, let's say here are these 2 Z checks. they were perfect for a while, and then they both changed. Now, what is a likely error that could cause it if an X error happened on this qubit at this point in time? Right? So this line denotes a possible error that could have caused this pair of defects. Now, now that's similar as the error that we've seen before. It's an error on the qubit. But now let's look at this one, where for a while the syndrome was +1, because we assume it to be +1 at the bottom, and it doesn't change, and it changes here, and it changes again there. So what is more likely going on there is that this bit was just faulty, right? The syndrome is faulty, changes again, back to being +1. So we can match these two defects in this way, by vertical lines. Yeah, so the idea is that if we now note where the syndrome changes values, these are now our defects, and we have to pair up these defects in this three-dimensional way by having vertical or horizontal, or partially vertical or horizontal chains of minimum weight. There's another picture showing the same, but now showing kind of a one-dimensional projection in the space. So these are -1 syndromes, and the black lines are possible errors. And now the black lines can be horizontal lines, which are the usual errors on the qubits. And if they're vertical lines, they are parity check measurement errors. So for example, this, here the syndrome was -1, and that was caused by this black thing. So we need to, yes, okay. So that gives you some idea of that. The noise threshold that has been estimated is also a number that is not fixed, because it depends a little bit on what you assume. First of all, it depends on what you assume to be the failure rate of the parity of the syndrome checks. You can say, well, okay, I have a parity check measurement, and with some probability Q, it's wrong. Yeah, and that Q is equal maybe to the Z error rate. That's typically the assumption that's made. Whether that's justified or not, of course, is the question. And so you see that this 11% that we had before is now reduced to something like 1%, which is still very good. It's among the highest of any code that we know. The thing, I'm not sure, I think I didn't show this, but one of the problems, I've done some study of various codes, and one of the problems that the surface code has is that for small l, the logical error rate is not very small. So you can say, if I, how do you say? So okay, so we made a plot where you say, okay, how many additional, let's start with some basic error rate. And then I make a plot of what my overhead is, how many qubits do I use, and what logical error rate do I get back for that. Then the surface code actually does not perform very well. And this, of course, is not so nice in the sense of that if you want to do experiments, you start with some small l. But you can say, well, if I start with some L is, or N, the 1313 code, which is about the smallest code, what is the logical error rate given some base error rate? And this logical error rate may not be very good, may be smaller than this base error rate, but only for larger L do you get better logical error rates. Okay, but here actually, well, here there's an estimate for L is 6. That's coming from this graph. This is something about Fowler, where he looked specifically at the surface code, at some depolarizing channel, and this is D is 6, and you take it to be over here, and you get a 10 to minus 7. So this is some kind of idea of how much overhead you expect, how big does the surface need to be in order to get some improvement. So L of 6, of course, sizable. It's 36 qubits. Okay, so now I want to discuss briefly how one does the... so I said the Hadamard and the CNOT can be done by code deformation. So what is that idea? And specifically, I want to say something about how one does a CNOT, because that's an idea that came about after this Dennis paper and was first cast in the language of cluster states. And it's an idea by Rausendorf and Goyal and Harrington, and has then been further advanced by Horstman and Fowler, and so on. So so there are actually two ways to do CNOTs by code deformation. And one way was the way that Rausendorf et al. Imagined this, and the second one is more recent by the Horstman and so on. And I probably going to be running out of time a little bit. Till what do I have now?
You've got half an hour.
Okay. So the first coding scheme is a bit inefficient in terms of space overhead, but that extra space may also lead to a lower logical error rate, so that is hard. But it uses two types of qubits. And these qubits are, so this surface is like the surface code, with these rough boundary and the smooth boundary here. So it's represented schematically. But these things, they're holes in the surface. And what does it mean to have a hole in the surface? It means that there is just an area where you don't measure the parity checks. And there are qubits inside which are just set to 0 or plus. They're disconnected from the code. I'll say something about how you make this hole. And this is two holes, and it has a smooth boundary. That's just, and this one has a rough boundary. And this is a double smooth hole qubit. And in principle, by having one hole, I could actually encode one qubit. But the way it's going to be done is that I'm going to use two holes to encode one qubit. And then the logical operators of that qubit, and maybe that's the thing that you have to remember, are the following. The logical operator of one, or the logical z, is a string of z's around this hole. Because now that becomes, before, if there's no hole, that was a trivial operator. But if there's a hole, then it's a non-trivial operator around the hole. And the logical x is a string of x's connecting these two holes. And I have a similar but sort of dual picture for the for this. This is the double hole rough qubit, where the logical z is this. So this we call a smooth qubit. This we call a rough qubit, and the quality of those qubits is determined by how large this hole is, of course, because that is the circumference of this, is the weight of this logical z, and the length of this. And it's also assumed that these holes are far from the boundary. Because otherwise, actually, if they're close to the boundary, then the logical x is something where, say, logical, if this one is close to the boundary and that one, logical x is actually equivalent to a line that, a brown line that goes here and a brown line that goes there, the product of these. And that can be, the thing is, that can be deformed away from the boundary. Okay, so the rough qubits, they will be used to do a CNOT on the smooth qubits. So they're sort of helper qubits. Let me see. Which slide? This? The one before. Yeah, so the rough, I will show you. So the idea is to actually you want to do CNOTs between the smooth qubits, but you actually do a CNOT between the smooth and the rough qubit. And then you have to do some tricks, and I'll give you a sketch of that, to do CNOTs between two smooth qubits. Now, okay, so one thing about why a hole, just a small thing about why a hole makes a qubit, very simple. Let's imagine I have a simple sheet It's actually, it could be the Toric code, but let's say it's just something without any, no periodic boundary conditions, and there's no rough boundary. And such a sheet actually doesn't encode any qubits. One can double check this. And I take out one plaquette operator from the stabilizer. That's an operator that commutes with all elements in the stabilizer, and now it's not in the stabilizer anymore. So this is a logical Z of a qubit. And then I have to find its matching logical X. And that matching logical X is now, before, it can be a string of X's that goes through this hole. Before, I could not terminate a string here, because then it would anti-commute with that Z plaquette. But now I've taken out that Z plaquette, so I don't care that it anti-commutes there. So that's the logical X. So that's a bad new qubit, because its logical Z has weight 4. So then it's clear what you can do. You can make a bigger hole. So instead of taking out one Z, you take these 4 out and the X in the middle. So you take out a volume of plaquette and star operators in the middle, and their qubits, you just deconnect their qubits. And such a hole has a smooth boundary. That's why it's called a smooth hole. Right? If I just say, okay, I'm taking this whole thing and I take out these 9 plaquettes and there's 4 star operators in the middle, then I have a smooth, bigger hole. Yeah. And so, as I said, the logical X is a string to the boundary. Yeah. So I can do that similarly for a rough hole. You would believe that if I start taking out stars, a block of stars and so on, I do something similar. Now I could do that. I could take out 2 of these holes, right? 2 smooth holes. And now this is the logical operators of 1, and this is operator of 2, and so on. And so, in some sense, I have 2 qubits, 2 encoded qubits. Like I said, I only want to use one of them, so I'm actually going to define my new qubit to be the state 0, 0, and 1, 1 of those 2. And so I can decide what are my new logical operators. For example, the logical operator for this guy is now x1, x2 for that guy. And what is x1, x2? This one was x1, this one was x2. So x1, x2 is just a product. And if you have to think topologically here, but you can also verify it in detail, that you can deform these, you can move this thing here, and if they both come together here, they can be glued off the boundary, and they can connect these 2 holes. Yeah? So they become this, because that is actually then the shortest string. Because you could so you can code many smooth qubits. The nice thing about the smooth qubit encoding is that it's now independent of the boundary. Yeah? So you just put these double holes somewhere. Okay, you can still do a similar thing for rough qubits. And now the C0 that was proposed. Oh, that's this font problem again. Okay, so if we do a C0 between qubit 1 and 2, where qubit 1 is a smooth qubit and qubit 2 is a rough qubit. And we cannot do a C0 the other way. And the way we do this is a topological braiding operation. It's by moving this hole around this one. So it's by moving this smooth hole around this rough hole. Okay, what does it mean to move a smooth hole around a rough? What does it mean to move a hole? Well, it means that, what does it mean to be a hole? It means that these parity checks were not there. So if I move a hole, I have to change where I do my parity checks. Actually, the way I move it is I actually enlarge this hole to become some kind of elongated thing. And then I start measuring the parity checks here again. And then I leave, I don't measure the parity checks there. So then I've effectively moved my hole. So that movement of holes is a deformation of the stabilizer group, right? Because I change what are the relevant parity checks. So I change what is the code. But these are just sort of very, very much related code. In one code, the hole is there, and the other code, the hole is there. Okay, so now what one has to verify in order to understand that this is a C0, one has to verify these basic relations. So an x1 becomes, on the control qubit, becomes x1, x2, and a z2 on the target qubit kicks back a phase, becomes z1, z2, and these guys are unchanged. So now, let's give you the sort of idea. I think maybe in my review I say something more about it, or there's an exercise. If I move a hole, if I move these two guys, then of course the string is pulled along, right? It's topologically clear. And now, what if happens if I do this? This string. So let's say I move this hole through here, yeah. And this has this Z1 around it, and this has Z2. Then this string will become a Z1, Z2. Now, this is not, of course, this may not convince you. But if you, maybe in my review I have a few more things about it. Okay, but there is a way of understanding this C0 by just following what happens, right? Because you have something which is the Z2, which is the string connecting these two. What happens is that the Z1 gets pushed through it, so the Z2 becomes Z1, Z2. And something similar happens for the X1, X2. So that's that one. Okay, so that's a way of understanding the C0 in a topological way. But this seems very limited because what we've done is we've shown how to do a control gate from a smooth into a rough qubit, but not the other way around. So these gates actually all commute. It's just a bunch of smooth qubits, and they're all control qubits. They all act on the rough target qubits. So that's not yet doing a more, the general control knot that we would want. So they have a whole spiel about, how this can be represented. And I have a slightly different way of understanding this, and I think makes it very simple, is we just need a teleportation trick to understand how to do a C0 between two smooth qubits. So what we want to do is we want to do C0 between two smooth qubits. I want to convert the target smooth qubit into a rough qubit. Yeah? If I have a circuit for that. Then I do my C0, yeah? And then I convert the rough qubit to a smooth qubit. If I can do that, I'm fine. Yeah? So I need a circuit that converts a smooth qubit into a rough qubit and vice versa. And that circuit, of course, should not be using any tools that I don't have. Right? So these are the circuits. So this is a teleportation type circuit where I have my rough qubit here. It's the target, not the control of some C0, so that's fine. And I can teleport that state into there, and this is a smooth qubit. So that circuit converts a rough qubit into a smooth qubit. And similarly, I can convert by a slightly different circuit, which is sort of Z teleportation. These are 1-bit teleportation circuits. I can convert a smooth qubit to a rough qubit using this circuit. I can't use this circuit because it has the C0 the wrong way. Yeah.
But don't you then have a limited number of operations because you measure a hole every time, so you destroy a hole, if I understand that right? Or
I have to use.
Additionally, add some new holes then.
No, I have to. It's like I have to use some extra supply of qubits. So, in principle, I want my computation just to be done on the smooth qubits, right? But I sort of need some ancilla rough qubits. At least I have. I start with my smooth qubit. Let's see. Okay, so down below, yes, I start with my smooth qubit here, and I convert it to a rough qubit. So I needed to have that rough qubit hole around, yeah. And then I take my C0, do it on my smooth qubit and my rough qubit, yeah. And then I need to convert this rough qubit back to my smooth qubit. But wait a moment. Yes. Yeah. Right. So then I've done this C0, right? So I've converted my rough qubit into my smooth qubit.
Yes, but what happens to this rough qubits that you use in Toric?
Oh, well, they'll just around. It doesn't matter that there are extra holes around in this surface, right? So I imagine I have a huge surface, and they're just holes lined up, and these are all my data that is lined up. And if they're sufficiently separated in terms of space, then the presence of this double hole does not affect any properties of whatever happens further along. Yeah, because it's logical, the logical X and logical Z, they're defined locally there on this hole. And that's true if this is sufficiently far from the other one. Because if it's close, then I say, actually, it's much, well, yeah, then it may be more problematic. Okay. So the second coding scheme, so that came about more recently, has some other interesting features, or its coding scheme. So in this coding scheme, we just encode a single qubit in terms of a patch, a surface code patch, which is in principle not even connected to other patches. Because if we don't need to do C0 gates and so on, we don't need to connect it. And if we have it in storage, we can just keep it separate. And the advantage of this scheme is that the encoding is much more efficient, because I can encode a single qubit in such a patch, and I don't have any, this other encoding. I had these holes, and it had to be doubled, and so on. And so in that sense, there's less overhead. Now, I'm not going to show how to do a Hadamard gate, I think, because I want to get to the end. So, okay, so what is the idea of doing a C0 in this fashion? So, we use this circuit identity. This is not in that paper, but I think this is a better way to understand it. At least I didn't understand what they were doing. So this circuit identity actually is an exercise in verifying this. I want to do a controlled knot between this qubit and that qubit, and I'm going to do it by having an ancilla in the state 0 and doing a projective measurement of the XX operator. So I project onto it being +1 or -1 eigenvalue, and the resulting state. Now, this circuit identity is only correct modulo Pauli corrections on control and target qubit. So I'm not denoting that here. So in order to do a controlled NOT gate, if I can show you how to do these two measurements, then I'd be fine. Because I think I already sort of at least argued that on a single sheet, one can do a measurement in the X basis. And so these are the ones that we have to do. And the way we do that is by lattice surgery, by merging these two sheets temporarily. And so that again, you can be viewed as a code deformation. So let's imagine these. So there is these two sheets, and the logical X of both of the sheets are this. So of this sheet, it's this, but of course it's equivalent to an operator here. And of this sheet, it's this line on these qubits. So these blue dots are the qubits, and these pink qubits, they are in beginning. They're just qubits, they're sitting there, they're disconnected. And we start by preparing these pink qubits in the state 0. And then we do something that one can define as a merge between those two sheets. We are going to measure the check operators in this region. Now, before we measured the weight 3 checks here. And now we're going to make these into weight 4 checks that involve this 4th qubit. Now, if everything was okay, these weight 3 checks had +1 eigenvalue. This is in the state 0, so it also has +1 eigenvalue. So the weight 4 checks will come out to be +1. And similar here. And now we also need to measure the x checks. The x checks are these on these. So these are new operators. We measure these 4 guys. So weight 3 at the boundary, and then weight 4 in the middle. So what are the answers for those? Well, in principle, they seem rather random because these are qubits in the 0 state. But there is one property that you can observe of this. If you take the product of all these checks, so I hope that's clear. So the product of the check here and the check there and the check there, then it cancels on this line, and it is x's here and x's there. So it's actually the product of these x check measurements is has the value of the product of the logical x's, because it's the product of the 2 lines of x's there. So what we get from this, they have these random values, but it actually, that measurement, if we take the product of the outcomes, it determines this value. Then we could, we could correct these values, but at least we have done the measurement that determines the eigenvalue of the product of the 2 logical x's. But now we've ended up with one big sheet, because now this is so that's not so surprising, because we have kind of projected the 2 qubit state on, an eigenstate of the XX operator. But now we'd like to split the sheets again. So we need to do a further code deformation by which we decouple the pink qubits, because we basically reverse what we've done. We measure them in the z basis and stop measuring the x checks at the boundary. And you have to be careful, it's not entirely true, to say, well, nothing bad happens with this eigenvalue of this xx, right? So you should not be doing something that doesn't commute with this. And again, all measurements, everything you do a step or you do something new, you have to repeat it L times to get a robust, outcome for doing noisy error correction. Okay, so that was a rough merge, and you can imagine you could do something similar. Instead of measuring the XX operator, you measure the ZZ operator by doing a different merge. Okay, so the Hadamard gates, let me see. Okay, yeah, I think I wanted to make one comment about this overhead. So, so the overhead we saw before was something like for general computation, we had originally have a circuit with n gates or n locations, and using the fault-tolerant circuit would have n times log n to some power locations. What does this look like for the surface code? Just for quantum memory, no gates. So for the surface code, we imagine that we want to encode k qubits, and every one of them will be encoded in an L by L patch, like one of these sheets. And the total noise rate, the logical error rate of those k qubits will go like k, because they're k qubits, times the logical noise rate for every one of those qubits, which scales roughly like either minus some, I don't know why it's called alpha prime, but some alpha times L. Goes exponentially down with L. And which implies, of course, if I want this to be some small epsilon, it implies that L should scale like log k, and therefore for k qubits, I will use this many qubits, k times log k squared. That is not a constant overhead, as you observe. and that there is a the surface code is in many ways you also can note that it's LK squared. It's not, it's not. It would be nice if it's linear in log k, but that's not the case either. And we see in general there is what we've proved that for two-dimensional stabilizer codes defined on two-dimensional lattices, we know that the surface code is generic in terms of a trade-off between the total number of qubits. So let's imagine I want to encode k qubits into n, and I want them to have distance d. And we can prove that for general stabilizer codes on two-dimensional lattices, we'll have this relation. So for example, if for the surface code of k is 1, then we see that d squared scales with n. So we see that d is the square root of L, which confirms what we have for the surface code. So there is an interest in seeing whether we can have codes for which such trade-off does not work, or codes for which even we have a constant overhead. No? And these are codes. We should not look for such codes on two-dimensional lattices. We should look for them in higher dimensional spaces potentially. And so there are some codes that were recent research, which I think is quite interesting. They are what we would call quantum LDPC codes. So the LDPC stands for the fact that the parity checks act on order 1 qubits, and each qubit is involved in order 1 parity checks, which is, of course, interesting for practical reasons. But the codes are defined on a 4-dimensional hyperbolic surface, but they do have the property that they have a good rate. And what does it mean to have a good rate? Is that the rate of a code is just k over n. Yeah? So you could look for versus what you would like of the best performance of a code would be something where the distance over the block size. So you have a general code that encodes k qubits into n, yeah, and each qubit has distance d. And what you would like, or the best performance would be something where you'd have both these parameters be lower bounded by some constant. So the rate would be constant, and the distance would also be some distance versus block size would be constant. Such codes exist. For classically, they're LDPC codes, and they even have very efficient decoders. And we don't know whether such codes exist quantumly. And in particularly, what we see for many codes is that the distance scales at most like the square root of some block size. But I also said the distance is not everything, so you have to be cautious. Maybe this is actually not so bad in terms of the performance of such code. But we also like a code where the rate is constant. So there were some recent codes that were defined that would allow for, in principle, a constant overhead in terms of if you would use those codes for quantum memory. But what I would find interesting, and I had a student in Aachen look into this, what are explicitly, this is quite an interesting construction, but we'd like to know explicitly what are the parity checks, and what is the rate, and what is the overhead of this code. If there's any chance that this is interesting from a practical perspective, right? Not just from a mathematical perspective.
From a practical perspective, can one, I don't have intuition one way or another of what it means to, in the usual surface code, there's all this locality. Is it in a two-dimensional code? How does one realize a four-dimensional hyperbolic?
Well, the thing is, one does need some long-range connections. and long range. And so the question is then whether you can do something with, like in the superconductor, you have cavities and you have, the question, you need maybe some photons that, make connections. Or there are other couplers that are longer. They also imagine that there are couplers that go outside a 2D plane. That is something, but not in 4D.
But not just some. The parity checks are low density, but the connections
Yes.
from
So
a two-dimensional perspective are quite high density.
right. It's a question of. Yes. I don't. Nobody has looked at this, and I think it is. You can have some non-local connections or long-range connections, but indeed, if it's a full four-dimensional space, it may be very hard to do that. Yeah. But I think it is. It's an open question whether there's any practical interest in that. Yeah. Okay. So now I think to conclude, sort of on a kind of a provocative note, perhaps, is that so I've been interested in quantum error correction, quantum fault tolerance, and then more recently I tried to think about how this can be done in experiments, and then you actually get quite pessimistic, I think, because you can dream up nice math, but it's very unrelated to what can be done experimentally, and so I want to give you a few, problems that I at least see, or to summarize the problems I see, which are some of their very different nature, that make it very hard to realize real scalable quantum computation and realize error correction through the path that I have discussed. There are other ways people think about it, and I think actually more people should be thinking about this. So the first thing is this overhead size problem. So that can be a problem in terms of how many, so you got your 1 qubit going, your experiment, and then you tell the experiments that you have to have 100 of them in order to have 1 logical qubit, which is better. And this is just, this is huge number. It takes a huge infrastructure. For example, like in the superconductors, cavities are order 1 millimeter. And there's just, in terms of space, and there are also components of this that are not so easy to imagine that you have hundreds or thousands of them. That is, and it's just it's a technology question, but it's an interesting question because it may also lead you to other, different hardware and control hardware that is interesting by itself. The accuracy threshold problem is that even though, like say, the surface code has a high noise rate, tolerates 1%, you say, well, I'd like to be safely below this 1% error rate. Yeah? And so and imagine that I do my parity checks with using 4 C0s, and the C0s, or the 2-qubit gate, I'm not sure David said much about that. The error rates they have, it's quite hard to push these up to, very, very low error rates. So they're like order 10 to minus 2 currently. And, can we get them really to this high, low error rate?
I'm not sure what you mean by
Yes, sir.
that. The 1% is an error rate per gate, right? It's not per syndrome measurement.
Yeah, but it's usually assumed that the 1% you have the probability of which the parity check measurement fails is the same as the basic error rate on every qubit. That is assumed in the 1% calculation. Or you think you also get a 1%.
Well, I think it means 1% in each C0 gate and each preparation and measurement.
Is really the... Okay, maybe I underestimated this. Okay.
So you'd really like to get like a C0 gate.
Okay.
10
10. Okay, so that is... Yeah, okay. Fine, thanks for... Yeah. Okay, so it's a little bit less, but still 10 to minus 3 is hard to get, because it's not impossible. But the thing is that at that level, if you see what approximations go into representing a 2-qubit gate, or modeling what we actually do in the experiment, you can ask whether the approximations that we usually do are going to be problematic when we want to go to this high fidelity regime. Usually way we model in physics, the experiment is done, and we say, well, we want to get an approximate modeling of what we do in order to understand what happens. But for this enterprise, we want to do something different. We want to be able to show maybe that we can get to this, very low error rate. So like the rotating wave approximation and things like that. One has to be more careful, and I think to work in this high fidelity regime is actually interesting for theorists to see. Theorists are needed to model the experiments in a much more accurate way in order to understand whether one can reach these low error rates. Okay, so the other, the control line problem is also, again, a practical problem, is that it also relates to calibration. As said in electron spin experiments, the qubits need to be calibrated, at least requiring individual control fields, which then can sit in the way, can take up space and sit in the way of coupling these qubits easily to other qubits nearby. For example, exchange interaction between electron spin qubits is order nanometer, but then the way they have experiments now, they have these contacts, gate voltages all nearby, and then if you imagine that you have to have many of the electron qubits, then these gate voltages are plainly in the way of also coupling these qubits with their nearest neighbors. And this is also in order to do the gates, there's always external pulses that have to be applied through lines that have to come on the chip. So that is demanding. And then there is the thing that is more pure theory work where you can say, how can we shave off this overhead of doing realizing a universal set of gates for stabilizer code? Because I didn't actually show this, but there's these hundreds of ancillas that you need in order to get one logical gate. And how much can we improve on that? And there's been some more recent work on that, and maybe there are even cleverer ideas to pursue in this direction. Okay, but I just want to think about these things, and maybe you have some response to it as well. Okay. That's all.